Um, so good morning, everyone. Welcome to the GIS Sea Level Rise seminar. We're very glad to have Dr. Emilia Kyung Jin, who is Director of Department of Policy and Partnership and Principal Research Scientist at the Korean Polar Research Institute. And her research interests include future prediction of climate change and extreme events based on ice sheet modeling, climate modeling, and climate predictability. She is an expert member of the National Response Council of the Intergovernmental Panel on Climate Change, a group leader of the SCAR Instant Clip Ant, and principal investigator for the Forecast of Antarctic Sea Ice Trends Research and Development Project started this year. Recently, she received the Presidential Award in recognition of her contribution to national science promotion from the government of the Republic of Korea. And prior to joining her current institute, Dr. Jin was an assistant professor in the Department of Atmospheric, Ocean, Earth Sciences in the College of Science at George Mason University, Korea. And she received her BS in Atmospheric Science and Master and PhD in Environmental Science from Seoul National University. And I know it's very late in South Korea, so thanks for joining us at this time. So welcome, Dr. Jin.
Hi, good morning, everyone. Actually, for you, for me, actually, it is midnight. Let me share my file at first. Can you see that? Okay. All
Yes.
right. Yes, great. Hello, everyone. As Patrick just introduced, I'm Emilia Kyung Jin from COFRI. I'm really delighted to have this chance to speak with you today. The title of my presentation is Improving Sea Level Rise Projections by Enhancing Surface Melting Processes in Antarctic Ice Sheet Studies. And this research was carried out by myself together with my postdoctors in Bak, Hyunjuri, and Eun-Suk. The impact of climate change are truly serious, and the reports show that more than 210 million people have already been displaced because of it. And as you know, one of the first direct impacts of climate change to create climate refugees sea level rise. For example, Pacific Islands like Kiribati are already shrinking, and then these countries are increasingly demanding about some international solution as climate change gets worse. And since over 40% of the world population live within the 100 kilometers of the coast, sea level rise is definitely one of the most critical consequences of climate change. And I'm sure many of you here today know this better than anyone. And actually, sea level rise is also a major concern in East Asia, including Korea here. In particular, the IPCC Comprehensive Report, Synthesis Report, released in 2023, described the sea level rise as an unavoidable, reversible, and abrupt change in the summary for policymakers. But there was also very hopeful message, like although the sea level rise can't be stopped completely due to the greenhouse gases already emitted, if we reduce carbon emission, we can slow down the rate of sea level rise. But anyway, up to today, the rate of sea level rise is accelerating as global warming speeds up. And the main cause is shifting from the melting of mountain glacier for the last century to the melting of Greenland and Antarctica for this century. According to the IPCC sixth assessment, the sea level could rise by at least 50 centimeter and up to the 1 meter by 2100. However, as you know, if the impacts of Antarctica melting, which are not fully captured in the current climate model, are realistically included, the sea level rise could be exceed 2 meters by 2100 and can go on and on. And the right panels, this wide range in projection happen because our understanding of sea level rise processes is still limited, and the models don't simulate them well. In particular, a poor understanding of ice sheet behavior is the biggest reason for uncertainty based on these papers. So that's why accurately predicting how fast ice sheet will melt is one of the most important part of sea level rise projections. At COPRI, we are conducting field investigation in key area of Antarctica and using the data to improve the ice sheet model and make better sea level rise prediction. Our sea level rise research, which began near Jangbogo Station, here in close to the Thwaites Glacier, has expanded to the Thwaites Glacier area, one of the fastest melting glacier right now. And then just before introducing the more result, let me briefly introduce COFRI. We actually operate 2 Antarctic research stations, Sejong on King George Island and Jangbogo Station in Terra Nova Bay in Ross Sea. And we are Korea's national organization for polar research and infrastructure operation. And that this building is us in Incheon, Korea. And COPRI was established in 2004 as a government-funded institution under the Ministry of Ocean and Fishery. And our annual operating budget is around USD 106 millions. And we have over 400 the research and technical staff with diverse expertise. And we operate 2 year-round Antarctic stations and 1 Arctic station and 1 ice-breaking research vessel right now. And our Arctic base is located in the Svalbard in Norway here. And then you already seen our 2 Antarctic stations here and here. And then our icebreaker, the Araon, has been operating since 2009 and is actively conducting the polar research, going the both Arctic and Antarctic area. And then we are also building a second icebreaker, which will be twice as large as our own. And we signed a contract with a shipping company actually this month, and then it is scheduled for completed in the 2029. So we have a much better the ice-breaking facility and much better equipment inside of this ship. So we have very big hope about that. And then come back to our research. The melting Antarctica is accelerating, as you know, and especially in the West Antarctica and that region. We are also targeting the Thwaites Glacier region, like the other groups in the world. And there are 3 main regions for Antarctic ice loss: relatively warm ocean water causing the sub-ice sharp melting like that way, and then warm air leading to the change in snowfall or surface melting, and finally the ice shelf breaking off through the calving event. And among these, the sub-ice shelf melting is currently the biggest driver of Antarctic ice mass loss. And unlike Greenland, Antarctica hasn't yet seen a large increase in atmospheric temperature, so sub-ice shelf melting has been considered the dominant process, and observational data support this, like that from the IPCC special report. However, looking into the future, by 2100 or even 2300, Antarctic air temperature are expected to become warm enough for surface melting to play a significant role, we think. Yet, most Antarctic ice model don't include this process properly, we think. So that's why in our study, we aim to refine projection of sea level light from melting of the Thwaites Glacier by including a parameterization for surface melting. Here's a brief. Our objective of this study is to evaluate sea level rise of Thwaites Glacier with current climatology and also simulate future projection of Thwaites Glacier, considering the realistic ocean parameterization and surface melting processes. And this is the domain for our ice sheet model. And here a brief overview of our experiment. We obtain atmospheric and oceanic forcings from IPCC semi-physics scenarios. So those are the emission scenarios, first the Earth system model, and then after getting the output, we are using those output as a forcing for our ice model like that way. So using these, we land the regional ice model for Thwaites Glacier to estimate the sea level rise from each future mass change. So we are also making very high resolution ice sheet version based on the ISSM ice sheet model. And the first using this, we ran the regional ice model for Thwaites Glacier, and then first we analyzing the characteristics by comparing the data from 5 Earth system models with observational data set like that way. Those 5 models actually have, we selected this model because those models have a long projection up to the 2300. For future projections, we used the ISSM Aishin model and running it with the forcings from the DH5 model up to 2300. And here are very simple experimental design here. The experiment including the cases with and without surface melting. So we noted this simulation as a non-step experiment which having the no surface melting, and CEB step experiment with surface melting. And we are using semic parameterization. I'm gonna explain you later more about that. And then we also compare the low emission and high emission scenarios from the SSP 126 versus SSP 585 up to the 2300. And those are the notion for the 4 different kinds of experiment. And then here are 5 models we used. And then we incorporated the surface melting by applying the semic parameterization, which originally developed for Greenland and we implemented this to our Antarctic model. This simplified equation uses several indicator variables to realistically simulate the surface melting, which certain advantages and limitations. So of course, we can get some surface melting, but it also can, disable to retain and percolate melting water through the foam layer, which is the cons of these parameterizations. And it also required a lot of daily data set from our system model, which it really take a long time for us to the process before running the projections. And then referring to the protocols from the experiment, like ISMI 6, we also adjusted the parameterization to better suit Antarctic condition like that way. So there are a little bit of change from the original code, and then also a lot of coefficient could be set or kind of the calibrating only for Antarctica here. And then for subsurface melting, we are using the PICO. While stable does have the downside of possibly underestimating the ice sharp method a little bit, but it is very stable parameterization, so we choose to using those one. It having kind of the full the effect are like the one-dimensional. So the melting is very kind of the linearly propagated through the ice sharp bottom line. And then this figure shows the comparison of key variables across the 5 Earth system models. And this is the surface mass balance, and these are the different the ocean salinity and temperature from the 5 different models. So mainly it is the important variable for basal melting in the right side, and then the left side is kind of the atmospheric forcing as a surface mass balance here. And then you can see the distribution from those 5 different models. But the clear thing is the differences between two emission scenarios. If you are using the ice melting and then also snowfall or so greater in high emission scenarios. So both surface mass balance is increasing for SSP 585, and then also the subsurface melting is increasing in the same emission scenarios like that way. And then finally, here are the our result, which is the sea level rise projection ovation model. And then this is the contribution from the Thwaites Glacier melting. And then if you see, the blue line is the low emission scenarios, and red lines are the high emission scenarios. So based on that, what it can really summarizing here is, without considering the surface melting, the global mean sea level rise by the year 2300 is projected to be a lower under the warmer scenario actually, comparing to the sustainable scenarios. Because when surface melting is accounted for, the grounding line of the glacier retreat more extensively under the warming scenario, leading to a significant higher global mean sea level rise. And then global mean sea level rise by 2300 without surface melting is like 66 millimeter for low emission, and then 29 millimeter for high emission scenarios. But if we including the surface melting, it changes to the 61 millimeter for lower emission scenario and 67 millimeter for higher emission scenarios. And then just until 2100, the surface melting is relatively very minor. However, after 22nd century, the surface melting significantly intensifies, eventually offsetting a large portion of the total snowfall. And then, but the thing is, while the impact of surface melting remaining limited during the 21st century, it significantly amplified ice mass loss and destabilizing the ice shelves beyond the 22nd centuries. Therefore, realistic projections of glacier behavior and future sea level rise must be simultaneously accounted for both the surface and sub-ice self-melting processes. And then so our study underscored the critical role of surface melting Antarctic ice sheet dynamics under the future climate change scenario and its potential contribution to global sea level rise. But one thing I just also want to emphasizing is the model's capability to simulating the snowfall from the Earth system model. Actually, as I said before, in the high emission scenario, the increase in snowfall is too large. So actually, it offsetting lots of the subsurface melting under the high emission scenarios. And then there are also research pointed out that the most of the CMIP6 model the overestimate the snowfall in Antarctica. So we thought for the next step from this study, we may try to analyzing the fidelity of snowfall simulation from the CMIP6 models. And then the next slide here, you can see the future projection of the surface melt using the CEMIC for each scenarios. The left panel showing the lower emission and right panel showing the high emission scenarios. And you can see the surface melting is kind of penetrating into the inland like that way. So actually just in terms of surface melting, definitely it's increasing under the high emission scenarios, but the snowfall also in the edge area is also increasing. So they are kind of the competing to gaining or losing the ice mass in Antarctica. And in particular, this study also highlight that in ice sheet model, the external forcings like snowfall largely determine the sea level rise projection. So this implies that the understanding the atmospheric and oceanic forcing is crucial. And that's why we also moving forward to the study the interaction between the atmosphere, ocean, and cryospheres. And I just want to show you several recent results about that. And this plot showed that atmospheric variability that affect the cryosphere, such as like ANSO, IOD, IPO, tropical variability, and through the teleconnection, it can change in the local circulation, on top of the Antarctica, and also interact with the ocean and sea ice. And finally, it can altering the melting rate of the ice sheet like that way, and then vice versa, the melting water from the ice also can alter the climate variability. So among those major climate variability, like El Nino, El Nino can affect the atmospheric over the West Antarctica, especially snowfall pattern. And then this figure explained a unique period during the 2015 and 2016 El Nino, when atmospheric teleconnection weakened the emergency low pressure systems, which we found like very interesting. And if you see, those are El Nino index like as a bar, and then those blue line is kind of the mass change in West Antarctica. And as you see, it reduced very fastly, but there are kind of the delayed signal in the 2015-16 year, which is related with the very strong El Nino year like that way. So as a result, if you see this map is like the El Nino driven 500 hectopascal GPH and precipitation, actually basically snowfall and vertically integrated moisture flux based on observations. So what he found out is as a result, the moisture flux from the middle latitude reaches deeper into the West Antarctica, leading to increased snowfall there under the very strong El Nino conditions, which is as a result of the weakening of emergency law here. So this temporarily slowed the mass loss of the West Antarctic ice sheet. So in summary, in Australia summer, when ENSO intensity is very strong, the teleconnection is weakened in the high latitude due to the absence of the subtropical jet, which amplify and guide the direction of wave responses. And on the other hand, in Australia autumn, the wave response to the ENSO becomes stronger and reaches high latitude owing to the appearance of the subtropical jet, which form a double jet structure with the polar jet here, so it can make those moisture flux to come into the West Antarctica like that way. So in fact, the phenomenon is very proportional to the strength of El Nino. If you see, this is the intensity of El Nino in x-axis and y-axis showing the snowfall anomalies. So when a very strong El Nino occurs, it can even appear as if the mass loss of the West Antarctic ice sheet is delayed because of the increased snowfall. But interesting part is to come later. However, the global warming could change this pattern according to the so this is the analysis of the different emission scenarios. If you see this map, the black is the observation and blue is the low emission scenario, red is the high emission scenario result. So when the global warming could, according to our analysis of CMIP6, if warming exceeds 1.6 degrees Celsius, which means the global mean temperature increase more than 1.6, even when an El Nino occurs, snowfall in West Antarctica does not increase. Instead, it appeared to accelerate the mass loss of the West Antarctic ice sheet, which can become a kind of the opposite side opposite sign of the variability actually. And then if you see the jet positions and those kind of the particularly integrated forward moisture flux, and then ASL anomaly, what you found out is actually the location of the center of the action of emergency low anomaly is going to the southward, but after the passing through the 1.6 global warming, it come back to the northward. So it really changing the response with opposite directions. And this map showing it very clearly. This is the global mean temperature, and this is the phologenic extension, and this is the position of El Nino driven emergency low anomaly. And last plot showing the position of El Nino driven emergency low anomaly, which is the south and north. And actually jet position and then anomaly west east position is linearly respond to the amplitude of the global mean temperature, while only north-south moving pattern of those wave pattern really having kind of the non-linear response like that way. So the 1.6 is kind of tipping point for this phenomena. The result indicate that the keeping global mean temperature below 1.6 is also very crucial to prevent this kind of reversion of the El Nino teleconnections. So after that, what you can say is the response of West Antarctic precipitation to El Nino is expected to weaken and disappear under the high emission scenario, with the precipitation anomaly even turning negative like that way. So the delay of the West Antarctic mass loss impact due to the very strong El Nino will be gone after more than 1.6 global warming like that way. So we found out this is kind of very interesting change of the regime due to the global warming, and then also those pattern could be a very important forcing of the ice model. So we analyzing this phenomena. And another thing is we also having some interest about like the East Antarctica, which also having some kind of small negative trend of the ice mass loss, like those Riksland area like that way. So we also analyzing the which part of the climate variability having some impact on those snowfall activities. So basically we look into that the atmospheric teleconnections, and as a result of that, what we found out is the Indian Ocean dipole is the primary factor reducing the eastern East Antarctica precipitation, while the SAM has localized impact only, and ENSO and the AMO has a very minor impact. So actually for East Antarctica, Indian Ocean have a very important role, and we actually having the more investigation for those subjects for the further research. And then I just want to introduce the kind of the new project we just starting here. It's a little bit different from the sea level rise, but actually also a little bit related because we really having the same observational field. Actually, for recently, Antarctic sea ice become very popular issue for, and then change in Antarctic sea ice area have a very significant impact on also Antarctic exploration and fishing basal route in for us actually. And is that sudden decrease in Antarctic sea ice because the complete melting of ice in front of Jambugo Station, which is located here. For the first time in 10 years, it have a 10-year of history, but for the first time, the sea ice in front of the station is melted out in 2022. So the sea ice in front of Jambugo Station is used as a actually runway for aircraft takeoff and landing for station supplies, a place for unload research vessels, and a place to observing polar organisms. So economic losses occur when the sea ice disappear. So the thickness of sea ice on Jangbo Station runway decreases earlier than usual in 22-23 seasons, reducing the number of flights into the Antarctic, and research activities are hindered due to the loss of sea ice in front of the station, which made loading unavailable. So in 2022, the cost of construction project actually increased by approximately 5 billion US 5 million, and then the project period was extended by 2 years due to the instability to unload at the Jangbo station, so it really causing the cost damage for us. And if you see, this is normal condition in 2021. The Jangbo station is blue, and the sea ice is filled even in the summertime. But 2022, it totally melted away. And then I just showing the video shoot outside of the Jangbo station. If you see, this video is just less than 6 hour long record. Less than 6 hours, the sea ice totally melted out like that way. And then actually we never expected and we never predict. And then, so this is the kind of region we're starting the new R&D project about sea ice. So the sea level rise study I just introduced to you is mostly come from the this project so-called KNOW, which the main objective of KNOW is to protect the sea level, the project the sea level change due to the Antarctic melting. And under the those project, we conducted the observation and then also prediction based on the ice sheet models. But after sea ice was breaking up in front of Jangbo Station, we starting the new project so-called FAST, the forecast of Antarctic sea ice trend. And then right now we starting kind of the observation of sea ice in front of the ice shelf, and then try to also working on the sea ice model, and finally try to making the snow forecast of sea ice. And this is also the WWRPP CAPS indoors project. And we are trying to making kind of the international collaboration network for this new project right now. And then the basic strategy is quite similar with the KNOW project. We're gonna do the field, the expedition first, which will be starting the next February, and then get some observation. Based on that, we're gonna improve our CIS model, and then finally we try to making the forecast. But in these cases, we also incorporating with the AI technique, which is the very promising and then very popular in crop space science right now. So as a part of this research, we starting kind of new study about fast ice. And as you know, fast ice is the ice that remaining stationary and attached to the shoreline or other fixed object like iceberg or shore. So in case of Antarctica, the fast ice is located in like that way. So it's also having very important role to stabilizing the ice shelf. So definitely it will be related with the sea level rise rate we believing. So as you know, unlike the pack ice which drift freely with the current and wind, fast ice stays in place, acting as a barrier against the movement of sea ice and affecting the flow of glacier and ice shelves. So as a first step of the fast ice study, we're starting like the analyzing circum-Antarctic fast ice variability. And this is the result we just tried to summarizing here. So this map showing like the this line showing the same index and then circum-Antarctic fast ice data set. Actually, recently, the Australian group, led by Fraser, made in kind of a long-term fast ice data set, which is covering the Pan Antarctica. It have 18 years of history. So we analyzing those data set and then comparing with the climate variability. So based on that, what you found out is those one. It does having some relation between these two lines. So actually, if we're regressing the same with the those fast ice variability, it doesn't have a very specific pattern having some impact onto the fast ice variability, especially those two regions. not a full region actually. Just these two regions having some kind of similar relationship with the SAM and fast ice variability. So in summarizing, the fast ice contribute to the mechanical stability of ice shelf and then improves coastal polynya size, size protection, and dense water formations. And then we explore the link between large-scale atmospheric patterns and circum-Antarctic fast ice variability, highlighting the how non-zonal SAM characteristic, if you can see here, in the Weather Sea and Amundsen Sea affect the sea ice and fast ice, particularly in the those two regions. So it means the same can altering the sea ice at first, and then sea ice change it can also having some impact to the change in fast ice only in those two areas. So this is the result, and we just try to keep singing about those variability, especially focusing on to the our station area covering the Ross Sea here. So here are my concluding remark. The Antarctic ice sheet, ice shelf, and sea ice remaining, some of the most uncertain element of global climate system, underscoring the urgent need for improving the modeling to better understand and predict their behavior. And our study, especially starting from the sea level rise study, which integrating the realistic surface melt permutation into ice model, has advanced the predictive capacity of future scenario, we think. Of course, there are still remaining parts improving further, but we try to step up from this point. And then we also look into the way to improving the forcing, including the climate variability such as El Nino and Indian Ocean dipoles. So those research is also sponsored by both two projects, which is the KNOW and FAST. And then I just want to share the one video, which is the after the sea ice is all breaking up in front of Jangbo Station. So we have a hard time to unloading the our supply to the Jangbo Station. Normally we just not using those kind of the small ship, but due to the melting of sea ice, we should using those small ships. So only just small container can be moved from the ship to the stations. So I just want to say this very abnormal state. And actually, 2023, sea ice never breaking up again. So we still having sea ice even, and then we expect to having the next year. But let's see how it turns out. Yeah.
Okay, thanks very much.
And that's it. Yeah.
Okay. Do we have any questions? Yes, Jeff.
Yes, thank you for the talk. But you suggested in the that you were not using refreeze, meltwater refreeze.
Oh, okay. Actually, this parameterization have a reprise part. So, based on the temperature and the other input variables, it can calculating those part automatically.
Does it do surface meltwater drainage systems and ponding?
Not that much. It just simply calculating the temperature, radiation, and then wind. And if we put those variables, it's just simply calculating like the surface energy balance. Yeah, but not really calculating the runoff or the other part under the ice.
So obviously, climate models with an inbuilt ice sheet will automatically do all that, and so they'll affect the ice mass balance accordingly. But I wonder whether a more important issue might be how to model the hydrofracture and associated with the surface melting.
Right. Yeah. Yes, yeah, that's a good point. Yeah, we can thinking about more incorporating like hydrological part into those precipitation. And then there are also the other student look into that like hydrological part to reflecting to the hydrology model to the ISSM, but we never really finalizing those part yet. So, but we try to incorporate in some point with those parameters.
Okay, thanks.
Ken, did you have a question?
Hi, Emilia. Thank you for that
Hi.
talk. I was on the Aron at Jangbogo in 2023. Also, it was a very nice cruise, and yes, the we sailed right up with no sea ice. I think my question was the same, which is why I lowered my hand, which is when you have the surface melting, that's a mass loss term. But the I guess sort of follow up to Jeff's question is it sounds like you didn't, or I'm not sure how that water was then treated in the model, but if that water stays on the surface and leaves, it's just mass loss. If it goes subglacial, then it's a dynamics component. And I'm wondering if that was included or if you think including that would, have a significant impact on future progressions and dynamic changes. Because in Greenland, it's the subglacial water which influences a lot of how the system behaves. And how much water do we need to start penetrating through the ice sheet as opposed to just running off the surface? And when do we cross that threshold?
That's right. That's a good point. I don't think Semi did have those part. It just calculating the surface, not really penetrating inside of the ice sheet. So which is unrealistic. I agree. We may try to thinking about how we can evolving from this point to make it more realistic. Yeah.
Okay. I mean, I don't know if it's unrealistic. I think it takes a lot of water to fracture open an ice sheet. So
That's
certainly at
right.
first it
Yeah.
stays on the surface, but
Yes. Yes.
okay.
Yeah, still there are a lot of unrealistic parts remaining still. Yeah.
Thank you.
Okay, any other questions? Well, if not, then I guess we can stop there. So,
All right.
so thanks so much again.
Yeah, thank you for inviting me for nice seminars.